So Microsoft has just released a new article about the Xbox Velocity architecture. This is going to be a technical talk, so let's dive in. So the author of the article is no other than Jason Ronald, the Director of Program Management at Xbox. So he's basically the lead on the Xbox Series X, Director of Program Management. So yeah, pretty big deal. So he's written a comprehensive article. I'll link it in the description below on xbox.com, titled Xbox Velocity Architecture, a closer look at the next gen tech driving gaming innovation forward on Xbox Series X. So with that, I'll basically just jump into some of the important things about what this velocity architecture really is. So firstly, Xbox Velocity architecture is thought of to be more like the soul of the Xbox Series X. The heart of the Xbox Series X is the CPU, the Zen 2 CPU with 8 cores, 16 threads, 3.6 to 3.8 gigahertz, depending on whether you have simultaneous multi-threading on or not. So that is the heart of the Xbox Series X. Then the Velocity architecture is considered to be the soul of the Xbox Series X. Before getting into the Velocity architecture itself, he goes on to praise a little bit some of the things that are impressive about the system. The fact that the Xbox Series X has got a 10 gigabyte GPU memory pool that is as fast as 560 gigabytes per second, the fastest memory pool around on any next gen console. So yeah, a lot of people like to tout a whole lot about the SSD with the PlayStation 5, and Sony did marvelous work with the raw capabilities of the SSD, but something that we always forget to highlight is just how fast the RAM in the Xbox Series X GPU is. 560 gigs per second compared to about 448, I think, in the PlayStation 5. So why is that important? The reason is because anything that has to be processed, whether it's to the CPU or to the GPU, first has to be sent into RAM. So instructions are not just sent to the CPU. They are not read from the hard drive into the CPU. They are actually loaded in the hard drive. Okay, rather they actually are loaded from hard drive to the memory, in this case the RAM. Okay, then from the RAM, then they are sent to the CPU. If we go in detail, even the CPU itself has some memory banks there. There's cache level 4, level 3, level 2, level 1 cache. So even from the RAM, instructions are actually sent into cache, and then from the cache into the CPU. So any instruction that has to be run has to go through a number of jumps before it can actually be processed, and that's a big thing. So the faster RAM you have, the faster you can feed the CPU so that the CPU is busy. A system can be slowed down by having slow RAM. Why? Because even if the CPU is as fast as it can be, even if it can be really fast, if the RAM is not able to feed the CPU with enough instructions per second, then the CPU will basically be idle. It will not be doing anything, and that's basically going to cause some performance drops. So having lots of fast RAM is very important, because the CPU will be constantly fed with things to process. So this is true for the GPU as well as the CPU. Then another thing that he goes on to boast about is basically the idea of the I/O. The whole I/O has been redone. The input-output, basically the way data moves around the system, has been redone. But to get into this, I'll just get into the Velocity architecture itself. So what is the Velocity architecture? So firstly, it's best to understand that the Velocity architecture is not one component, but rather a combination of both hardware components and software techniques coming together to give an experience that's ideally supposed to be better than anything that is out there. So the idea is the sum of all the individual parts is greater than the whole. So that's the idea here. The sum of all the individual parts is greater than the whole. So let's talk about the individual components that make up the velocity architecture, since we're saying it's actually a collection of major components, both hardware and software. So these four major components include the custom SSD, the SSD that Xbox Series X will come with. There's a hardware decompression block, the direct storage API in DirectX, and of course sampler feedback streaming. So the first two are hardware and the second two are software. So in this case, these are the four that make up the velocity architecture. So let's see what's special about them. I'll go in order of what I think is especially revolutionary. So this is basically how I'll go. So first up, the custom SSD. So the custom SSD is 2.4 gigabytes per second raw, as everybody probably knows by now, 1 terabyte, and is about 40 times faster than the hard drive in the Xbox One. And something that to note in here is that Microsoft is basically talking about the numbers that are sustained rather than the peak numbers. The article in a lot of places actually goes on to address this. So it is possible that these numbers could be higher. So in this case, 2.4 gigabytes per second could be considered conservatives, but I'll read the line just so that you guys can understand where I'm getting this from, right? So developers have a guaranteed level of I/O performance at all times that they can reliably design and optimize games around, right? The custom NVMe SSD in Xbox Series S is designed for consistent, sustained performance as opposed to peak performance. So that line right there is basically what we mean. So because with systems, with hardware in general, you have peak performance and you have the performance that's constant, the performance that's consistent, the performance that's predictable. This is normally because of heat, it could be because of power and other limitations on the system, such that if other variables are removed, performance can go up or down. This is basically easy to understand if you've seen CPU boosting, right? CPU boosts can go for a certain amount of time, running instructions at a higher frequency, and then you have the stable, normal, consistent and predictable performance. So the peak performance of a CPU boosting is not the same as its consistent performance. There's always going to be a point where you could hit into you could call it throttling, right? You could call it where it's going to basically stop, or it's not where it's going to be consistent, where it's going to be the same because of other factors around the system that are affecting it, such as power and heat. So in this case, the SSD is 2.4 gigahertz, 2.4 gigabytes per second, which is basically a consistent, sustained performance. So that's basically the idea with the SSD. Then the second part of the Xbox Velocity architecture is the hardware decompression block. So these hardware decompression blocks are very, very key because they allow the SSD to basically perform much more than it can physically do on its own. So the example that's given is assuming you have a 2-to-1 compression ratio. So assuming 2-to-1 compression ratio, so let's say you've got 10 MBs of files, right? 10 MBs of files, and then you want to compress and decompress them. So a 2:1 ratio would mean that a 10 MB file can effectively be double, right? 20 MB. So that's 2:1. That's the ratio that's there. So with Xbox Series X, you can effectively have about 4.8 gigabits per second in the I/O performance, rather than the actual 2.4 gigahertz. That's 2.4 gigabytes per second. That's on the hardware itself. So the hardware's physical limitations are at 2.4 gigabytes per second. That's the sustained performance that they predict. But in this case, the hardware decompression block is basically able to have compressed data, textures, and other factors like that, and then it could then decompress them as and when they are needed, so making it use a whole lot more data than it could have sent in the same amount on the same size of the bus. And it's also important to notice that the hardware decompression block on Xbox Series X has a general purpose algorithm, right? A general purpose algorithm for compressing and decompressing anything, things like game files, audio, textures that make up your graphics, and any other factors, right? Fonts, sounds, code, source code files, and so on. So there's a general purpose algorithm that's meant for compressing things that are not textures, all right? And then there's a specific BC pack. So BC pack is particularly meant for compressing and decompressing textures. So while I do not have the numbers for how BC pack does in comparison to the normal decompression and compression of other things, it's interesting to me that Microsoft has two different algorithms for compressing general things and also for compressing textures specifically. Textures are the larger part of your game because they form your graphics, your player, the trees you see, the road, all of those are textures. So the textures are the larger part of your game. The source code, the audio, and all of those, they are large, but normally not as large as the textures. A 4K game is normally going to be large because 4K textures are huge. So it's interesting to see that Microsoft has actually decided to have BC pack, a specific algorithm that's meant to handle texture. I'm yet to see a comparison on how this is going to perform in regards to having them compared. If we compress a 10 MB general purpose file versus a 10 MB texture file, is there a difference? There's probably a reason why they had two algorithms in the first place, right? There's probably an advantage of having BC pack when specifically working with textures. Otherwise they would have used the general purpose compression and decompression algorithms. So we have specialized hardware for decompression and compression. And a key point to notice is that with this decompression block, you basically have performance that would have been able to 2 Zen CPU cores. So if we did not have these hardware accelerated decompression blocks, the hardware would have been using part of the CPU cycles on the Zen 2 CPU. By having these decompression blocks, we offload some of the work from the actual CPU, meaning the CPU will be left to handle other things, meaning that it's likely to be more efficient at those other things because it will have less to do. Okay, so that's 2 of the 4 components, so the SSD and the hardware decompression block. The third important thing is that you now have a new API. So an API is basically an application programming interface. Programmers work with these whenever they are working with software, when they want to tap into certain features and so on. Now, this is direct storage. Direct storage is part of the DirectX family, DirectX 12 Ultimate particularly. And if you know anything about DirectX is what basically handles your graphics on PC and on Xbox. Sony have, especially that they work with the open source, they're probably working with things similar to Vulkan, but I'm not sure the actual one. It could be a custom solution, but probably based off the Kronos group. So in this case, this new direct storage API, why is it important? Why does DirectX need a direct storage API? So the idea is the APIs that we use for working with data, passing data from one part of the hardware to the, especially the GPU, these are based off of really old technology, old techniques. They have not undergone any changes. In the article it says for about 30 years or so we've been using the same ones since the early versions of Windows. Basically, they've not had any major changes. So because of this, everything that happens on the hardware level, you can have a really fast SSD, but it's working with old APIs. You can have a really fast SSD in terms of the hardware, but on the software part, the software can also limit how it handles those read-write operations. Okay, so that's the idea. So again, they've not given us any numbers about how fast this direct storage API helps. Why is it particularly more important than using the traditional APIs that have been used in prior years? So in this case, all that they can say is that it helps working with prioritization, handling multiple queues, and even latency. So I'll talk about each one of them to perhaps give you an idea. So prioritization means what's needed first, what's needed right now, right? So data that needs to be processed immediately needs to be sent as fast as possible. It needs to be sent quicker than data that will be needed in the next 3 seconds. That's the idea. Then latency is basically delay. Okay, how long does it take to have data from one area to another area, from the hard drive maybe to the GPU or to the compute units, the CUs, the ones that actually process the graphical instructions. So that's the idea. So with latency, of course, with most devices, these are really low numbers, but when you're talking about programming, graphics and things like this, a millisecond of delay can change a whole lot of things on the higher level. Okay, so it means in this case that they are reducing the latency. So it actually says minimizing I/O latency. So because they've reduced the latency, then we could assume that data is able to move quicker, or at least data that needs to be processed as fast as possible will arrive there with less delay. Then establishing multiple I/O queues. So we have a couple of queuing disciplines, especially in networking. FIFO, first in first out, weighted fair queuing, and other queuing techniques like let's say first in first out. Then you have weighted fair queuing, and I've forgotten the third one. I can't remember it. But the idea is that depending on how you handle queues, so if you have first in first out, then everything, all data basically is going to be processed in the order at which it arrives at the CPU, right? So the order in which the instructions call out specific aspects of the data, that's basically what's going to determine what data will be processed first and what will be processed last. In things like weighted fair queuing, you have data that basically is weighted, and by weighted we basically just mean that some will be regarded more important or others will be regarded as less important, and so the ones that are considered more important will be sent to the CPU much quicker than the ones that are supposed to be sent, the ones that are not supposed to be sent immediately, the ones that are not considered important. So you treat data differently depending on the classification. Alright, so in this case we basically have something that's not a FIFO queue. So they could be using a weighted fair queuing mechanism for processing data. So these three, I think, are the main aspects of the new direct storage API, which should make data that's needed by the CPU and GPU significantly faster to access the moment it's needed. And this is basically, I'll read a quote from the article that says, resulting in virtually eliminating load times for fast travels that are just that fast. Okay, so then the last component of the velocity architecture is the sampler feedback streaming. So sampler feedback streaming is my personal favorite of all the four. This is because it's, I think, a game changer. I think in the next few years this will be the big thing. I think we need more clear demos for what this can do when we're seeing a game running. So the idea with sampler feedback streaming is so when loading a scene, you have lots of things. So let's say you're playing a game and you're in a game world. Let's assume you're playing a first-person shooter, and behind the mountain there are enemies waiting for you, right? So when the game loads, the game loads up everything that's needed in the scene. All MIPs, all textures, all of them are going to be loaded in memory. But based off of what Microsoft is claiming, they are saying that by assessing the way the Xbox One X GPU was working, they were able to realize that the Xbox One X GPU, so the part that actually processes these textures, was only accessing less than a third. Okay, that's maybe just above a quarter, right? So the GPU was actually accessing less than a third of all the texture that was loaded in memory. So if you have your RAM, right? So we're saying we have a 10 gig RAM chip, that's 560 gigs per second, right? And let's say we're playing Red Dead Redemption 2, and we are in this nice open world, right? And we are riding our horse, going over the shores and stuff like that, right? So the game itself could have loaded and filled up all the 560 gigs, right? I mean all the 10 gigs inside the GPU memory, right? But in terms of usage, the GPU would only be processing about a third. So a third is like 33% of all the loaded memory. Now remember, when starting out in this article, I mentioned that for anything to be processed, it has to be sent in the memory, in RAM. Okay, so if I want to see something on the screen, it has to come from the hard drive, jump into the RAM, then from the RAM to the CPU and the GPU, and then I have an output on the screen. Now what this means is that a game that's basically running and has no sampler feedback streaming, a console that does not have sampler feedback streaming will have a lot of wastage. Particularly 66% of all the data that will be loaded in memory would not even be accessed by the GPU. So in short, you would be wasting 66% of that 10 gig. Alright, so PlayStation 5 has 16 gigs of RAM, right? So does Series X, but Series X has 10 gig that's ultra fast, and then a more moderate 6 gig. But let's say with PS5, right, you have 448 gigabytes per second. So what this means is that if our game has used up all the RAM, right, if we've loaded all the RAM, the system has loaded all the textures, all the audio files that are needed to be played as you play your game, the GPU and the CPU are actually only going to be using 33% of all of those things that have been loaded, meaning 66% is actually filling up the RAM and not actually being used. This is what's making this groundbreaking, because at sampler feedback streaming, the GPU will only pull the data that it needs to work with. That's the game changer. So because of this, I'll read a quote here, okay, about what this innovation results to. So this innovation results in approximately 2.5 times the effective I/O throughput and memory usage above and beyond the raw capabilities on average. So that's an interesting quote and is a big changer, a big game changer. So if you don't have any way to think of it this way. If I need to load a 9 gig file, right? Okay, so if I'm on PlayStation 5 and I'm running a game and my game wants or the system needs 9 gig of RAM, right? Only 3 gig of RAM is going to be used by the GPU. Okay, at least this is based off of what the Xbox One X analysis was like, right? So the system will call for 9 gig, assuming that all 9 gig would be used. But depending on what you do in the game, you might change direction, point your gun to the other side, and move to the other side. The other things that were loaded in memory will never be used, maybe because you've gone into a different room than what the game was assuming you would do, you would get into, right? So a lot of things are loaded in the GPU space, in the GPU memory space, because it thinks you're going to actually use them, but they never get used. So with this feature, the GPU only pulls in what is needed. It only pulls in the things that you're going to be needing to work with. So this is basically sampler feedback streaming, and for me is, I think, the best feature of Xbox Velocity architecture. So when everything is considered together, the SSD itself, the hardware decompression blocks, the new direct storage API, and sampler feedback streaming, we have one hell of a system. We've got one hell of a system. So I can't wait to see what developers, particularly the big developers at Microsoft, would be, what they would manage to do with this. Because with sampler feedback streaming, in theory, okay, this is just a completely wild idea, right? In theory, a console that has much less memory would be able to compete with a console that has more memory, at least 2.5 times more memory. Why? Because the console that has sampler feedback streaming would only use memory it needs, while the other system that does not have sampler feedback streaming and does have more memory will be loading a lot of things in memory that will not be processed either way. So that's a game changer to me. Okay, so together, when all of these things are considered together, this is having a lot of impact on the overall efficiency of this box. So the example that they also give is the idea of being able to load 100 gigabytes of game data stored on the SSD just when the game requires it, right? Instant low-level access to more than 100 gig of game data stored on the SSD. This is because everything is working together. Remember, the SSD can only do 2.4 gig, right? Then the compression blocks can double that, right, to 4.8 gigs, right? But then you have direct storage APIs that can prioritize, include multiple queues for sending data, right? And then you have sampler feedback streaming that will only pull the required data, right? So even if a game is 140 gig like Call of Duty, right, not the whole 140 gig will be used. So that's why this is brilliant, and so it's going to sound very, very exciting, and I can't wait to see what more will be shown. So that's basically the Xbox Velocity architecture as explained by Jason Ronald, with my own examples based off of what I've read. So tell me what you think. Click on the like button if you enjoyed the video, and of course subscribe Leave a comment, leave a question, what do you think, and this will be that.